So let me talk a little bit about how the rest of our course is looking with these. I mean, we're getting really close to being done with this semester. Chapter 14 has 4 sections. They are the last 4 sections that we have for the semester, so for the course. With that being said, having classes virtual has really cut down on time it's taking to get through classes. Basically, because we don't have to take class time to do a quiz. We don't have to take class time to do tests, since they're all done outside of the class. And what that's done for us is it's put us pretty ahead, because we've just been kind of going on the normal schedule, but then we have all these class days that would have been taken up if we had been, normal um, class instruction, but we're not. So we have some extra days, and you'll be seeing an email about this from me. But while I've got you guys here, these 4 sections, so we do one today, one Friday, one next Monday, and then one next Wednesday. So basically, a week from today, we'll be done learning the material. My thought, and some professors are doing this because of everybody going all virtual after Thanksgiving anyway. And we've been virtual basically the whole time. I know that. But other classes have been in person, then they have to go all virtual. So they're trying to get things done early so they don't have to deal with that. And it is a possibility that we could get things done early, even though going all virtual really doesn't affect us, because we only have 4 sections left. My thought is possibly getting done before Thanksgiving. It is a very real possibility for us. It wouldn't really even require rushing anything or cramming things in, at least the way that I've scheduled it out, as an option. So it's just a thought I had that possibly we could get this class finished totally, like our 4 sections we have left. We do have exam 3, and we have the final, and that's it. And so that's just my thought as an option. I'll be sending an email asking you guys for input on that. I don't want you guys to feel overwhelmed or rushed. I don't think you would feel rushed really, because we only have 4 sections left and then those 2 exams, especially being able to take the exams outside of class would help a lot. But it's an idea that maybe we could be done with this class like right before Thanksgiving break. And then you could, spend your time and focus after Thanksgiving on finals for your other classes. So just a thought, I want you to think about it. I'm going to send an email, ask for input on that. But today we're going to be looking at section 14.1. And you'll probably be glad to hear that we're not doing antiderivatives anymore. So we took those 3 sections in chapter 13 to stop derivatives and go backwards. We talked about integration, doing antiderivatives, because it's important stuff to know. But you guys, in 14, we go back to being derivative driven. In 14.1, and a little background, all of chapter 14 is about multivariate functions. And in 14.1, we're not even really going to be taking derivatives or anything, you guys. We're just having an intro into multivariate functions. And then through the next few sections after this, we will work with multivariate functions, like taking the derivative of those, optimizing those, and so on. But here in 14.1, like I said, we're just introducing multivariate functions. So what is a multivariate function? Well, let's recall all the functions we've been dealing with. And basically, since you've been in algebra, the functions we look at are in one input variable. So we have, for example, f of x equals, whatever, x squared plus 2x plus 5. And you put a variable in for x, or you put a number in for x, and you get an output in y. So we know other than f of x, we could call our output y. And then when I put a value in for x and then I see what y equals there, we end up with ordered pairs in x, y. What do we do with those ordered pairs? Well, we can graph them in the xy coordinate plane and get whatever shape. But you guys, this, for example, would be a parabola. Two-dimensional shapes is what we get. Well, what we're going to be looking at is mainly functions with two input variables. So you're going to see f of x, y today. So for example, let's say f of xy equals 3x squared plus 2y plus 5xy minus y squared, something like this. You've got both x's and y's in your function, which means you're going to have two input values. The output, if I wanted to write it not in function notation, usually we call this output z. Because remember, we used to input x and get out y, but if we're inputting x and y, we need another variable for the output, and usually we call that z. So you guys, if I asked you to evaluate this function, I would have to give you values for x and y. So I might ask for f of 1, 2, and that would mean we're going to put we're going to put 1s in for all the x's, and we're going to put 2s in for all the y's. So I'd get 3 times 1 squared plus 2 times 2 plus 5 times 1 times 2 minus 2 squared. And then I just evaluate like normal. So you guys, that's 3 times 1, that's just 3, plus 4, plus 10, minus 4, and we get 13. So this says that when I put x is 1, y is 2, I get an output, or usually we call that z, of 13. So 1, 2, 13. Now we don't have an ordered pair, we have an ordered triple. 2 inputs and 1 output. So I can't graph that on my xy plane because it has 3 coordinates. You guys, your graphs for multivariate functions in 3 coordinates need 3 axes. So you guys, I'm going to apologize ahead of time. I'm not very good at drawing 3-dimensional space. I barely can draw 2-dimensional space. So, just, bear with me there. Pretend you can understand what I'm drawing. But you guys, to graph this point, for example, think about the x and the y axis. Like, think about taking those and maybe like laying them flat. Like, think of this as laying on a flat surface, and think about z as like a depth or a height, coming up out of the graph, or if it was negative, going down under. And on this particular ordered triple, 1, 2, 13, x is 1, y is 2. So you guys, we're going to have this point that if it was just flat, it would just be like right here. Like, think about this laying on a table. But then z is going to take it up. Let's pretend that's 13. It's going to take it up high, and it would actually be up here in space, in this space above the table, if you will. And again, just drawing a point in the plane isn't very, it's not very representative. It's hard to tell, especially just drawing it. If I had like cool graphics or something, maybe it would look like this point was raised up above the x and the y on the z-axis. But I think you probably get the point enough. So you guys, we're in 3-dimensional space. Let's look at another function. Let's say f of xy equals the square root of 2x squared plus y squared. You guys, these functions can look like all kinds of things. They can have roots, they can be polynomial, they can be rational, anything you could have done in just x, you can do in x and y. This wouldn't be a graph that I could graph for you with my limited skills. So I am not going to do that, and I would never make you do that either. But we could do some evaluation. You guys, what if I want to do f of -1, -3? Well, I'm going to have 2 times -1 squared plus -3 squared. And then just evaluate from here, you guys. So 2 times 1 is 2. This is plus 9, and I get the square root of 11. And I would just leave it like that because it's not a perfect square. So you guys, what would the order triple look like here? It'd be -1, -3, and then the z coordinate would be square root 11. Nothing too crazy here, you guys. I think this is going to be a nice, easy section. So you have these evaluating. So they're going to give you a function. You evaluate it at the values for x and y that they ask. You have quite a bit of practice on those. And then the only other thing that we do in this particular section is a little bit of graphing. And because it's on MATLAB, it's not like you are actually doing the graphing. What you're going to do is you're going to have like 4 graphs, and you choose the graph that is the function given. And I'm going to show you what kind of functions you're going to have to know what the graph looks like. We're going to basically be looking at linear multivariate functions. They're the easiest to graph. So when I say linear, in just one variable, usually we think if I have f of x, for example, equals, let's do 3x plus 7. I know this is linear because my x variable is only raised to the first power. That's how you know a function is linear, because the variable is only raised to the first power. I also know, here, let me put this in a y equals version. That's what we're used to when we graph lines. I also know that this graph's a line. So that would be pretty easy to handle in just 2-dimensional space. So you guys, let's talk about f of xy in a linear form. You guys, maybe I have 3x plus 2y plus 6. This is a linear multivariate function because I have x and y, that makes it multivariate, but they're only raised to the first power, which makes it linear. So if all your inputs are only raised to the first power, we're looking at linear. Now, the thing about these is because we're in 3-dimensional space, it doesn't just graph a line anymore. It actually graphs a plane. So a flat, like a, well, you know what a plane is probably. I don't know how else to say it except for it's a plane. Like a sheet of paper or something that goes on infinitely in all directions. So you guys, I'm going to write this in the other notation where I have the output as z. So I have z equals 3x plus 2y plus 6. Now, so you're going to see when you do the graphs, they won't be in function notation. You'll see x, y, and z. Because remember, when we're graphing lines, we usually look at the version where it's just y equals. Well, that's going to be the same here. Now, the other thing they're going to do when you're trying to graph these, it actually makes it a little bit easier, is that instead of having the z solved for over here, your equations are going to look more like this. So it might say 3x plus 2y, let's make this plus z equals 6. So changing this one just a little bit to fit the parameters I want. But you guys, so what they do, instead of having z solve for it, whatever constant there is in that function, they put that by itself. And you guys, notice that that mirrors the standard form of a normal line. So remember, when you're graphing just lines where your input's x and output's y, you might see something like 2x plus 3y equals 6, like that. That's a function that graphs in the xy plane. This is just a line. We called this standard form. Well, you guys, this is also standard form. It's just there's that extra variable in there. So if I wanted you to graph this function here, this linear multivariate function that's in standard form, well, I want to think about how I would graph this function here. How would I graph this line? What's the easiest way to do it? Well, the easiest way to do it is to find the x and y intercepts. That's how we did it in algebra when we had it in this particular form. You guys, how do I find an x-intercept? Well, I just set y equal to 0, and I would end up with 2x equals 6, and I get x equals 3. That's where it crosses the x-axis, and then I could plot that point, and then I could find the y-intercept. How do I do that? Well, to find the y-intercept, I would set x equal to 0, which would leave me with 3y equals 6 and y equals 2. I would plot that on the y-axis, and then I would make a line connecting the two. So it would look like x is 3, y is 2, and a line connecting. So that's probably the first thing we learn in algebra, right? How to graph a line using intercepts. Well, you guys, I'm going to do the same thing over here. It's just that instead of just 2 intercepts, I have 3. So how do you think I'm going to find the x-intercept of this equation here? Instead of just having to set y equal to 0, I'll set both y and z equal to 0. I'll end up with 3x equals 6 and x equals 2. Then I'm going to find the y-intercept by setting x and z equal to 0. I'll get 2y equals 6 and y equals 3. And then I have to find the z-intercept. And I'll do that by setting x and y equal to 0. And I get z equals 6, and I just get z equals 6. So if I were to try to graph this, all I would have to do is go 2 on the x-axis, 3 on the y, 6 on the z. And you guys, this would be a plane. And again, it's really hard to draw in a 3-dimensional space. But this plane is kind of going like out in all these directions. And you guys notice that if I cut it off, if I make borders for it using the intercepts, it looks like a triangle. So think about this triangle, and it's kind of like it's leaning a little bit, and technically this goes on in all directions infinitely. But in order for us to kind of understand or grasp what this picture looks like, you're just going to be having this triangular section. So think about this triangular section being a triangular plane, I guess. And you guys, this is what your graphs are going to look like in MATLAB. When you match the graphs, what you're going to do is you're going to find the intercepts, and they're going to have points graphed. So for example, this one on the x, it would be 2, the y, it would be 3, and the z, it would be 6. And you just find the graph that has your intercepts that you found. And like I said, they will be cut off into this triangular section of the plane. And the reason being is because in the directions, it'll say that we're only graphing what we call the first octant portion. So you guys, you might wonder what an octant is. Let me go back up to this XY plane I have here. In the normal XY coordinate plane, don't we have quadrants? We have 1, 2, 3, 4, and they happen because the axes create them. You guys, they separate our plane into 4 sections. That's why we call them quadrants. Well, you guys, when you have 3 axes and we're in this 3-dimensional space, the X, Y, and Z axes actually separate that space into 8 sections. So that's why we get octants. And you guys, you might wonder, well, what's the first octant? Why is this triangular plane what I get when I'm only graphing the first octant portion? Well, think about how the quadrants worked. In the first quadrant, didn't we find that both X and Y coordinates are positive in the first quadrant? What do you think is happening in the first octant, you guys? This is where X, Y, and Z are all positive. So this triangular shape, these lines that are connecting your intercepts are acting as borders for each of these coordinates. You guys, if I go, so notice this bottom border. If I went down here, that would be a negative Z value. If I went over here, this would be a negative X value. If I went past this border here, it would be a negative Y value. So if I say first octant portion, what happens is my borders get created between my x-intercepts, and I'm just looking at a triangular portion of the plane. So you guys, all you have to do is find the intercepts, pick the triangular graph that has those particular intercepts in the right places. So nothing too crazy, guys. Like I said, we're not taking derivatives today. Taking derivatives of these is a little bit different, but we'll talk about that next time. This is just getting you familiar, used to looking at functions that have more than one input variable. But that's about all I have to say about it. You're going to see examples that are just like the ones we did in your homework. I'll be putting that up here in a little bit. But yeah, so it's kind of a short lesson. And then next time, just make sure that you are comfortable with these multivariate equations so we can actually take derivatives of them. Also be thinking about what I said about finishing early before Thanksgiving. I want to hear your opinions on that and get feedback when I send an email out later today. Otherwise, I will see you guys back here on Friday.